So imagine you're standing right next to a massive wind turbine or looking straight into the gearbox of a high-speed electric vehicle.
Right, lots of moving parts.
Exactly. With thousands of pounds of torque just churning away, you would naturally expect this deafening, terrifying roar of metal tearing on metal.
Yeah, you really would. I mean, it should sound like a metallic nightmare, but it's often just a quiet, continuous hum. Right. And while that silence is definitely not an accident, it is a highly engineered illusion.
I love that phrase. So, welcome to our deep dive into the source material on precision transmission manufacturing.
Glad to be here.
Our mission today is to translate this dense engineering cheat sheet we have into the physical, gritty reality of how these unbreakable silent gears are actually made.
We're going to look past the basic geometry and really get into the extreme machining processes that make that silence possible.
Right, so let's start right at the beginning, getting that raw shape out of a block of steel using gear shaping.
Yeah, shaping is crucial.
Reading the source, it sounded essentially like scraping out the inside of a pumpkin. Because a standard bulky cutting wheel just, it won't fit into those weird interior angles.
No, it won't. You need a reciprocating cutter to actually get in there. You're relying on that shaping process primarily for internal gears or components where you have extremely limited tool clearance.
Right.
But shaping really just gives you the raw, blocky geometry. To get that smooth silence we just talked about, you have to transition to gear honing.
Now, I have always been a little skeptical about honing.
Oh, really?
Yeah, I mean, we're talking about massive heavy-duty machinery here. Does polishing out these microscopic surface grooves actually do anything, or is it just like engineering overkill?
Well, you have to think about the physics involved. At those incredibly high RPMs, every single microscopic imperfection on a gear tooth acts like a tiny hammer.
Wait, like a hammer?
Literally striking the mating gear thousands of times a second. So implementing gear honing fundamentally alters that surface texture to drastically reduce vibration.
Oh, wow.
Yeah, that is exactly how you eliminate that awful high-frequency noise.
Okay, so honing solves the noise problem. But before we even get to mass production, engineers have to prototype these highly complex profiles, right? And often out of extreme hardness materials.
Right, and you definitely cannot just hack away at those with standard tools.
No, exactly. The sources highlight wire electrical discharge machining, or wire EDM, which, reading this, it's basically cutting metal with a microscopic continuous lightning bolt.
That is pretty much exactly what it is. You are using a taut wire and electricity to just vaporize a perfectly clean path right through solid metal.
Vaporize, that is wild.
It is, yeah. It's the essential tool for R&D. Because by vaporizing the path, engineers can safely prototype intricate parts without the risk of destroying $1 million cutting tool on these extreme hardness alloys.
Right, but wire EDM is really just for that R&D phase. When you move to mass production and deal with pre-hardened metals, you have to actually physically cut it.
Yeah, and traditionally, once metal is heat-treated, you are sort of stuck painstakingly grinding it away.
But the cheat sheet says hard turning changes that whole equation.
It really does. It allows engineers to directly turn those heat-treated, hardened materials with specialized cutting tools. So you skip the grinding process entirely.
And by skipping the grinding, you're achieving incredible geometric accuracy, right? Like when you need absolutely perfect alignment for the bearing seats on planet carriers.
Exactly. Hard turning delivers that necessary precision directly on the hardened material.
Okay, so we've achieved perfect shape, perfect texture, and alignment. But none of that matters if the gear just shatters under the massive torque of that wind turbine.
Right. You have to stop microcracks from forming under all that pressure.
Which brings in shot peening. Reading about this, I thought of it like packing a snowball tightly so the outer layer doesn't just disintegrate the second it leaves your hand.
That makes sense, yeah. But imagine packing that snowball so densely that the outer layer literally turns into solid ice. Yeah, shot peening bombards the metal surface with high-speed projectiles. This physical impact induces intense compressive stress on the outer layer.
So it essentially compresses the surface so tightly that those microcracks physically do not have the space to open up.
Exactly. By compacting that layer, you drastically elevate the material's fatigue strength.
Right.
It's specifically applied to the most vulnerable areas, like the tooth roots of planetary gears, to meet these extreme reliability standards. It literally stops a gear from shearing apart after years of relentless pressure.
It is a physically brutal birth for such a silent final product.
It really, really is.
So next time you hear the smooth, quiet hum of an EV or a turbine, Think about the incredible journey that piece of metal took for you. It was carved out in tight spaces, smoothed at a microscopic level to eliminate vibration.
Zapped with continuous lightning during R&D.
Right, precision turned while hardened and physically bombarded with projectiles just to survive.
Absolutely incredible process.
Which leaves you with an interesting thought for the future. As additive manufacturing and 3D printing technologies become increasingly advanced, building parts atom by atom from the ground up,
Yeah, it makes you wonder.
will these intense, subtractive, and physically brutal finishing techniques eventually become obsolete relics of the past? Or will we always need to hit things with microscopic hammers to get that perfect engineered silence?